welcome to Swansea University for what promises to be, I think, a very fascinating lecture this evening. Now, we're also delighted to welcome our colleagues from the National Research Network for Low Carbon Energy and Environment. And as David has pointed out, this is a Pan-Wales initiative which supports collaborative research interactions at the interfaces between land, water, food provision, and provision of energy also. So this is the first time that we've hosted one of these events at Swansea, and sort of given the climate summit in Paris this week, we couldn't have asked really for a more timely and relevant speaker. Now, Dr. Vicky Pope is Head of Integration and Growth at the Met Office. So you're all familiar with the Met Office. This is the UK's national agency for meteorological predictions across the timescales. Now, this is from daily forecasts through to the effects of climate change going into the future. So it's not really just about how we can plan our weekends going forward in terms of the weather. It also does have a direct impact on maritime and aviation safety and routing, all of these things that we quite often take for granted, agricultural planning and flood forecasting. Now, this is in collaboration with the UK Environment Agency. But the estimated benefit to the UK economy that the Met Office provides in terms of its forecasting is around £300 million. So that's quite staggering. Now, the UK Met Office model is also used to provide projected future climate information to the UK government, but also to the Intergovernmental Panel of Climate Change, the IPCC. Now, this is to inform policy on climate change and energy, and to plan mitigation strategies for likely future climate scenarios. Now, all of this notwithstanding, I mean, Vicky, if you could really have a word and see if you could do something about the rain in Swansea, that would be very helpful. Now, Swansea University has a long-standing relationship with the Met Office through its work of the Global Environmental Modelling and Earth Observation Group, which uses satellite data to help improve weather forecasting and climate predictions. This is led by Professor Pete North, and the group uses observations from the Earth's land surface from spectrometers which are based on NASA satellites. Now, this is to refine the way in which the model can be used in order to predict the weather. And we're very proud that that collaboration has resulted in the implementation in all of the Met Office models since 2008. Now, Swansea's collaboration with the Met Office is ongoing, and therefore it gives me real pleasure to welcome Dr. Vicky Pope this evening, who will discuss how climate is affected by natural and man-made influences, and how these are likely to affect the weather and also the climate going forward, and also around our activity here in Wales. As Head of Integration and Growth, Vicky is responsible for maximising the benefit of the Met Office's science capability through identifying opportunities for cutting-edge environmental science to provide new and improved services in, for example, hydrology, transport, and digital economy sectors. Vicky joined the Met Office in the 1980s and obtained her PhD in meteorology from the University of Reading. In the 1990s, she led a team in stratospheric research and climate model developments. In particular, she led the development of the Met Office's Hadley Centre models used in IPCC third and fourth assessment reports and for the UK climate projections released in 2009. In 2002, she became a senior manager of the climate research programme for governmental departments such as the Ministry of Defence, the Department of Energy, Food and Rural Affairs, and also the Department of Energy and Climate Change, ensuring, and this is very important, that the Met Office provides climate change science to underpin policy development. For example, she led the Met Office contribution of science to the Stern Review on economics of climate change and worked on improving communication of climate change science. So, ladies and gentlemen, we're in excellent hands this evening. Please welcome Dr. Vicky Pope, whose talk is entitled The Weather and Climate and How It Will Change in the Future.
Thank you very much. It's good to be here. Sorry I didn't bring better weather with me. So I'm going to talk about climate change. I'm going to show you some observations of climate and how it's changed already, and then how it will change in the future. But to start off with, I just was going to say something about what weather, climate and climate change are, because there is often a confusion about these things. So this is a quote that a lot of people attribute to Mark Twain, but in fact he never actually said it, but he did say something rather similar. Climate is what we expect and weather is what we get. So what that's saying is that climate is about the average of the weather. It's about not just the mean, but also the variations in the weather. So, you know, how often you get storms, but not each individual storm. And weather is the individual events. So when we talk about climate in the 2050s, we're not telling you what the weather's going to be on the 25th of June in 2051. We're telling you about what those variations are going to be like, what the average is going to be like. So we're already seeing evidence of climate is changing, and I'm going to show you that in a minute. And this means, of course, that we no longer know what to expect. So we can look at the past and say, you know, we've seen extreme events, or we've seen certain things happening. And the same sort of thing will happen in the future. Well, now that the climate's starting to change, and change more rapidly, then we're starting to see more and more records broken with things like heat waves and heavy rainfall. And so we're moving towards uncharted territory. And we're seeing changes in the number and frequency and strength of weather events over long periods of time. So, how does the climate machine work? So, I think I show this photograph because it illustrates very clearly one of the problems of actually modelling the weather and climate. You know, if you look at the complexity of those cloud structures there, and you think that you're trying to represent that in a model, in the sense of a climate model, you might only have you divide the world up into grid boxes. The grid boxes might be 60 kilometres across. You imagine trying to represent all of that, that wealth of physics going on in those clouds in that kind of context. So you have to parameterize a lot of the processes that go on in the atmosphere. You have to average them and represent them in an approximate way. And that's one of the challenges of climate modelling. And so I'm just going to describe to you the kind of basic physics of what goes on in the climate system and the things that we need to represent. But I just wanted to, you know, use that image just to illustrate that all the time we're having to make these sort of compromises. And this means that we need to test our models very carefully to make sure that they are actually reproducing the essential features of the real world. Because we know that we're approximating, they're not going to reproduce everything. But if they don't represent those key features, then we won't have confidence in our projections. But we do feel that we represent enough. So the climate system is a finely balanced system, and it relies on a number of cycles that interacting and giving you this kind of balance. And what we're doing by changing the greenhouse gases is changing that balance. And I'm going to go through each of these in turn. So we'll start with the energy cycle. So essentially, the climate system is driven by the energy from the heat from the sun. So you've got incoming energy from the sun, and some of that is reflected by clouds. Some of the energy is reflected by the earth, and some of it is absorbed by the atmosphere and by the earth, of course. So there's complexity going on there. And then, as the Earth heats up, of course, it then re-emits energy back into space. So you're absorbing wavelengths in the ultraviolet, and you're emitting them in the infrared. And so you're getting some of the energy is going back out to space. It's passing through some of it's passing through the atmosphere, but some of it, of course, will be, you know, absorbed by clouds and by the greenhouse gases in the atmosphere. Some of it will be reflected back to the Earth. But in essence, the whole thing has to be in balance. So, you know, when you look at the top of the atmosphere, the amount of energy coming in will be the same as the amount of energy going out. It has to balance. But what's happening here is that a lot of that activity is happening around the greenhouse gases, which effectively, they act a bit like it's not quite like a greenhouse, it's a little bit more like a duvet, actually. And they act to trap the heat in the atmosphere. So in fact, if you look at the signal, when you increase the greenhouse gases, you get more heating low down in the atmosphere, but actually it's cooler higher up in the atmosphere because that heat's being trapped in the atmosphere. And so gives you the current structure, and as the greenhouse gases increase, they act to change that. But it's really important to recognise that actually having greenhouse gases in the atmosphere is vital for life on the planet. So if there were no greenhouse gases, the average temperature of the Earth would be minus 21 degrees centigrade, so all the water would be frozen and there would be no life on Earth. With the greenhouse gases, it's 14.5 degrees. So, and it's that, and obviously the life is contributing to that, to the carbon dioxide in the atmosphere. So it's that balance that gives that, that the kind of richness that we get in terms of the world's climate. So, as part of that, a really important part of the climate system is the water cycle. So as the surface heats up, water evaporates from the rivers, lakes and oceans, and also from the land surface as well. The water, as it rises, it cools down and condenses to form clouds. Some of the water also you're getting lost from plants, soil, animals and people, so it's the way that the surface releases water will depend on the nature of the surface, the land surface, and all of that we need to represent in the models of the climate as well. And obviously the water returns to the land as rain and snowfall. It's carried downhill by rivers and seeps into the ground and flows out to the sea. So you're getting this cycle of water. And a lot of course, the water is coming from the oceans, is evaporated from the oceans. So you can see that cycle working. So that's a very important part of this. I should also mention that water vapour is also a greenhouse gas. So whilst we're not actually changing the water vapour directly by what we're doing in terms of pollution into the atmosphere, there's a feedback process. As the greenhouse gases go up, the temperature goes up, you get more evaporation of water and the water cycle becomes more active. And on average, you have more water vapour in the atmosphere and more rainfall. You actually end up with, because the cycle is more active, you actually end up with less rainfall in some places, where because it's dry in some places, and more rainfall in other places. So that extra water vapour in the atmosphere acts to increase the warming. So you're getting this positive feedback where you get extra warming because of the water vapour feedback. The clouds themselves can also have an effect on the climate. So some types of clouds cool climate and some types of clouds warm climate. So if you look at, you remember that photograph I showed you, that kind of richness of cloud behaviour, you have to represent quite a lot of that behaviour in a climate model in order to get the climate change right. If you think about what happens on a cloudy day, it tends to be cool because not as much sunlight's reaching the surface. So that's an effect that cools the surface. But if it's cloudy at night, then actually you can trap heat released from the ground, so you're not so likely to get a frost. So you can see immediately that those sorts of things make a difference. And it also turns out it makes a difference whether you've got low cloud or high cloud, and the thickness of the cloud has an impact as well. So all of these things we have to capture. And so I should say it's also, as well as getting the modelling right, we, in order to get that modelling right, we have to have very good observations of clouds so that we can actually assess the models. And you mentioned earlier about some of the Earth observation work that's done here. That these sorts of pieces of work are really important to help to evaluate and improve our models. So the other aspect of all of this is the general circulation. So basically because you've got a differential in heating between the equator and the pole, you're going to get the movement of the air and the movement in the ocean is going to redistribute that heat. So it's basically trying to reduce the temperature gradient between the equator and the pole. Because obviously the poles don't heat up as much from the sun as the equator does, and so you get these series of circulations that appear around the globe, and the complex weather patterns that arise from those temperature differences. So that's all affecting that rebalancing. But I've talked about greenhouse gases, and so you can see now that as all of this is in a fine balance with a very interconnected system. If you change any one of those elements, then you're going to change the way that balance works, and that's what we're doing by changing the greenhouse gases. In the past, if you look in prehistory, then the things like changes in the orbit of the Earth have changed the temperature. And that actually feeds back on the carbon dioxide, and it's driven through a change in temperature, and you get this positive feedback process. But what's happening now is we're actually changing the greenhouse gases, and that's driving the change. So there's just a summary of all of those processes. So what's the evidence that we see that the climate is changing? So this is the carbon dioxide record, so going back to the 1950s, and you can see you should be able to see, certainly if you're near the front, that there's a variation from a seasonal variation across the year, but there's a very clear upward trend in carbon dioxide. And so the basic physics tells us that we would expect the climate to change, the temperature to change because of that. So CO2 has risen by 38% from pre-industrial levels. Methane, which is another greenhouse gas, has risen by 150%. It's an extremely potent greenhouse gas, but it has a much shorter lifetime than carbon dioxide. And it arises from changes in land use, for example, but also that it's another feedback process. It can be released, for example, when permafrost melts, it can release methane and CO2. Just to contrast, at the end of the last ice age, CO2 doubled over 5,000 years. So what's happening is we're changing the greenhouse gases in the atmosphere by large amounts over relatively short periods of time, and that's where obviously we need to be concerned about the changes. So I'm going to show you a series of different weather sensitive measures now, which all indicate that the climate is changing. It's not just about temperature, surface temperature. So this is land surface temperature. The different coloured lines on there are different analyses of the global temperature record. So there's a number of groups that do their own analyses. And you can also look at the uncertainty range of those. I'll show you a diagram that shows that in a minute. But you can see there that you've got lots of variation from year to year, quite a bit of variation from decade to decade, but particularly since the 1950s, there's a very clear increase in temperature. And essentially, decade on decade, if you look at each, average each decade out, you see that there's been a consistent increase in temperature over the last 50 years, consistent with the basic physics. And here we have the sea surface temperature. The changes aren't quite as rapid because the ocean takes longer to warm up than the land because of the heat capacity of the ocean. But what you do tend to see is less variation from year to year because, again, the ocean responds more slowly, so you can see the long-term trend more easily in the sea surface temperature. This is the tropospheric temperature. So this is temperature in the atmosphere, not at the surface. Now, we don't have records going back as far. We have balloon measurements here, and we also more recently have satellite measurements. But to go back 150 years, you have to look at surface records. Obviously, we don't have satellite measurements going back past the 70s, really. Specific humidity, so that's the amount of moisture in the atmosphere, the amount of water vapour. So I talked about the fact that we'd expect that to increase as the temperature increases, and indeed we see that. Again, there are very big variations from natural variations as well, so distinguishing the climate change signal is more difficult with water vapour. Sea level rise, so again, as the heat goes into the ocean, basically the water expands because it's warming up, and so the sea level is rising. In future, we also will expect to see additional sea level rise because of ice melting, and there I'm talking about the freshwater ice, places like Greenland, glaciers and ice sheets, and Antarctic. It's more the ice sheet, the ice sheets in Greenland that are likely to have the impact over the next 100 years. We think that Antarctica is less clear that it's going to have much of an impact on that timescale, partly because there's actually at the moment very little precipitation in Antarctica. It's quite dry, and as the warming increases, you'll get more snowfall, and so in some parts of Antarctica you actually get increases in the amount of ice. And so it's less clear exactly what the signal is going to be, although I think it's very much an area of active discussion about how much the Antarctic ice will change in the future and how quickly it will change. So this is just the Arctic sea ice extent. So this is now the saltwater ice. So this is over the sea, And that melting doesn't have an impact on the ocean because it's already in the ocean. But it's one of the clearest signals of climate change, because the Arctic actually responds more quickly than other parts of the globe. And so if you're looking at trying to look for strong signals of climate change, it's a good place to look. And so we've seen an area of the size of Greenland disappear in the last since 1979, which is when the satellite record began. So again, glacier mass balance, you can see a decrease there. Again, getting a global measure of that is quite difficult. There are now satellite measurements which allow you to do that, but they're relatively recent, so it's quite difficult to get a clear signal from that. So we can use models to help us to actually work out why these changes are happening, to try and to make the links between the man-made greenhouse gases and what we see in the real world. So this diagram here shows the 20th century global mean temperature. The black line is the observations, and the red line is the average, and all those little thin lines are all the different models. The red one is the median model. And what you can see is if we include all of the factors that we know about, then we can reproduce pretty well what happens in that global signal. It turns out we can also reproduce some of the major patterns of climate, of the changing climate as well. So it's not just a question of getting the global average right, we're also looking for these patterns. If we just use the natural variability in our model, we don't get the increase in temperature in the latter half of the 20th century. So you can see immediately, just by looking at that in order to reproduce the signal, we can't explain it unless we include the man-made changes. I should say, so when you look at the patterns of change, we're looking for, we call them fingerprints actually, we're looking for a fingerprint of change, because carbon dioxide has a particular pattern of what you'd expect to see. If you look at something like aerosols, which act to cool the climate, they have a very different pattern. They tend to last in the atmosphere for only a couple of weeks, so you tend to see the aerosols where the polluting is happening. So you see very large amounts of aerosol, for example, over China, and India, Northern Europe and America, less so because they're pollution controls. But so you can see there that the patterns that you see are very different. And so we look for those fingerprints, again, to assess how the climate is changing. So do we know what to expect in the future and what we're seeing? So this now is bringing those diagrams up to date. This is the temperature record right up until September this year. And what you can see, you may have seen it reported in the press recently, that for the first time, the global average temperature is 1 degree warmer than it was in pre-industrial times. Now that extra little bit that you're seeing there is, sorry, I should just the second arrow there, is because there's a very strong El Nino. So in a year or so's time, that will come down again. So it won't stay at that very high level. So, because what you're seeing then is this strong variability. We had a very strong El Nino in 1998, and if you look at the Global Warming Policy Foundation website, which is a skeptics website, you'll notice that they show a temperature record from 1998 onwards, and they draw a straight line, and they say global warming has stopped. They haven't actually updated their record for this year yet, so I'm not quite sure what they're going to do with that. But it does just illustrates that you can't just, you've got to be careful how you do the statistics, because there's lots of things going on short timescales, and you need to make sure you distinguish what is actually a climate change signal and what's a natural variability signal. That's just to illustrate that. So in that sense, you could say that we're halfway to 2 degrees, but it's that the increase in this year is obviously temporary. But when you look at sea level rise, so this now is looking at a much more local sea level rise. This is actually in Cornwall. And you can see even, somewhere on a small scale like that, you can see a signal of increasing sea level. But the sea level rise that you see is only a third of the global sea level rise you'd expect at 2 degrees centigrade, and that's because it takes longer for the sea level rise. It takes a long time for the ocean to warm up, so it responds more slowly than the temperature. So it's just an illustration that not everything in the climate system changes at the same rate or in the same way. So it's not a linear process. So what about carbon cycle and how that affects things? So the CO2 emissions are the red curve here, And the black line is the actual CO2 growth in the atmosphere. So the atmosphere is, so not all of that CO2 is ending up in the atmosphere. Some of it is going somewhere else. And essentially what's happening is some of that's being absorbed by plants and the soils and also by the oceans. And so that's, if you like, buying us time. It's actually taking away some of that CO2, so the warming is not happening as quickly. And it's also, I mean, in the short time scale, actually increased CO2 helps plants to grow. So in some situations, it's actually beneficial. It's only once you get to the higher climate change where the increases in temperature actually outweigh the impact of the increase in CO2. But the other thing to bear in mind here is that the periods where the CO2 in the atmosphere is largest is where you've got warm years. So this is an illustration from observations, nothing to do with model projections, that illustrates that relationship between CO2 and temperature, that there's a feedback process that means when the atmosphere is warmer, the biosphere is less able to absorb the CO2, and so you end up with more of it in the atmosphere. So this is a positive feedback. So it's positive in a scientific sense, not in a impact sense, of course, because it's actually making the climate change worse. So as temperature goes up, we expect more of the CO2 to end up in the atmosphere. We won't be able to get rid of as much of it. And so the warming will accelerate. And this is just an illustration of that. And that process is captured in the models as well. So are there changes in the number of extreme events over periods of time? So these are examples of extreme events that have happened in the last few years. This is actually a picture from Welsh coastline of flooding in 2014. I particularly like the picture of yellow taxis, which is in New York, which was after Superstorm Sandy. It's just to illustrate that the impact of climate change is not just about developing countries. It's not just about what happens in Africa. It does actually have an impact in places that you would have thought would be resilient to the weather. But it's not to say that any of these events are caused by climate change. So were they caused by climate change? Well, no, you couldn't say an individual event is. But what we're looking at is that it's more, it's getting increasingly likely that these sorts of events will happen as the climate changes. And for example, if you look over the whole of the Northern Hemisphere and you look at the incidence of extreme rainfall, sort of very heavy rainfall events, we're seeing an increase in those extreme rainfall events. And there is some indication that some of that is due to man-made climate change. And as we go further in the future, we would expect that to change more. So all of these sorts of things are likely to happen more. Just to mention the cold winter, which you might think it's a bit odd that I've included that here, but there are also some indications that on a kind of medium time scale that actually climate change could paradoxically give you more colder winters over Europe, because there's some indication that as the Arctic sea ice decreases, that can have an impact on the weather across northern Europe, so the large-scale weather patterns basically, which could give rise to situations where you actually end up with colder winters. So another aspect of this kind of variability is that the jet stream that comes across the Atlantic, which brings with it all the storms, that tends to move about during the winter. So if it's to the north of the UK, we tend to get dry, cold conditions. If it's across the UK, we tend to get the sort of wet, windy weather that we've been having over the last few weeks. And what could happen is, as the temperature gradient between the equator and the pole decreases, because the pole warms up more quickly than the equator, that actually that jet stream gets stuck more often in one place. And so you end up with longer periods over over the winter, where that jet stream stuck across the UK, and you get a series of wet, windy storms, which is what we had in 2014. And then other periods like 2010 where it stays in one place. So it's possible that actually you could get these sorts of extreme events which actually last over a period of time because of this change in the behaviour of the weather. And we're only really starting to understand those things now. Now we've got faster computers, we're able to run models with much higher resolution where we can capture these processes better, which we haven't been able to do before. So this was a piece of work that was done to look at that 2014 stormy winter, and they looked at whether you could attribute some of the signal that they saw to human-induced climate change. So the prevalent southwesterly flow over the UK in the winter of 2013-14, which provided favourable conditions for extreme rainfall and extreme winds. Here we find some evidence for a human-induced increase in extreme winter rainfall in the United Kingdom for events of timescales of 10 days. So that's just the kind of first indication that this kind of thing is already happening, and we're seeing those signals. So what about the future? So this is a standard IPCC plot of the change in temperature in the future. A lot of the diagrams in the IPCC report relate to global averages, and it's very hard to relate those global averages to what happens, in Wales or America or wherever. But it's a kind of basic step that we have to take. So if we continue to increase greenhouse gases at with a fairly high emission scenario, which we're currently on track along that emission scenario, then we would see temperature rise of 4 degrees possibly by the end of the century. You notice that there's quite a wide, it fans out quite a lot because obviously there's a lot of uncertainty in the projections, and they reflect those in the report. If we're able to peak emissions within the next few years and then decline very rapidly, and in fact, in some suggestions that you might even need negative emissions to get that scenario, then obviously you can keep the temperatures below 2 degrees. But it's an extremely challenging scenario to meet. And in fact, I think for the next IPCC report, they're going to try and look at actually unravelling what that scenario means. They started off from a premise of the radiative forcing, so it was a kind of scientific thing, and then work backwards to get the emission scenarios. But actually, you've really got to look at realistic emissions to get something that's useful to policymakers. So this is just a summary of the sorts of changes that you'd expect around the world, and I'm going to show you 2 of these, one for 4 degrees and one for 2 degrees. So this is that red line up there. So what does the world look like at the end of the century? So we're looking at temperature rises of, in the Arctic of 12 plus degrees. When you look in the tropics, you're looking at something more like 3 or 4 degrees, and in some, inland in some of the continents, you're looking at 8 degrees. So this is just on the average. And then if you look at how that impacts on other things, so obviously you'd expect more heat waves. You're also looking at things like methane release. So as the permafrost melts, I mentioned that methane, carbon that's trapped in the frozen tundra, as that gets released into the atmosphere, it can be methane or carbon dioxide, depending on whether it's aerobic or anaerobic. But that will then again feed back and increase the warming. Obviously, you'd expect to see melting ice. There are indications that we'll see stronger tropical storms. You see reductions in crops in most regions, probably when you go to 4 degrees. At 2 degrees, you tend to see improvements in crops in some regions. So in this part of the world, for example, it would be easier to grow crops because there'd be more CO2, and of course you've got, at a moderate level of warming, you can grow different sorts of crops. It's possible that you might get rainforest loss as you get drying. Obviously, forest fires can be increased. I was just talking to somebody about this over drinks beforehand. But if there's questions about how forests will change. So all of these, and then of course there's as the CO2 is absorbed into the ocean, that leads to ocean acidification, which has major implications for life in the oceans. So this is a much more boring picture, which shows the impact of a 2 degrees centigrade rise. It was quite interesting when we produced that 4 degrees centigrade plot. Everybody said to us, "Oh, you must produce a 2 degrees one. It's really important that you have that." And when they looked at it, they said, "This is a bit dull." But that's kind of the point, really. So you get some of the impacts, but obviously they're much less, and in some cases you actually get some benefits. So, but clearly, if you're living in a small island in the Pacific, you probably aren't really interested in those benefits with the impact of sea level rise. So this is a piece of work that was done in collaboration with a number of other groups for the Department for Energy and Climate Change, looking at avoided impacts essentially, and saying, if we are able to reduce emissions so we can control the temperatures at 2 degrees, what impacts do we avoid by doing that? And so it's looking at water availability, crop yields, a whole range of things. And it's saying between 20 and 70% of the impacts can be avoided by staying within 2 degrees. It's not just a question of the impacts being twice as bad at 4 degrees. Some of the impacts are much more amplified at 4 degrees than at 2 degrees, which is kind of what you would expect, I think. You wouldn't expect those sorts of complex things like crop yields to be linearly dependent on temperature. It's much more complex than that. So how can we change this? So we've used 2/3 of the emissions. If we want to keep at the levels to keep temperatures to 2 degrees, you need to look at the cumulative emissions of CO2, because the carbon dioxide stays in the atmosphere for such a long time. It's really the accumulation that's important, because it's not disappearing after a few weeks, it's staying there for 100 years plus. And so far we've emitted 2,000 gigatons. There's a lag between the emissions and the adjustment of the climate system, so even if we stop emissions today, we'll still see further increases in temperature. So we're committed to further climate change from what's already been emitted. And obviously staying within 2 degrees means limiting the total global emissions to 2,900 gigatons of CO2. So what does this mean for Wales? So this is I've just picked out the Wales part. This is these UK climate projections that were produced in 2009. And the one on the left is the projections that we produced in 2002, and this is looking at changes in rainfall in summer. And you can see that the original projections that we did, where we were only able to do one because we only had the computer to do one for each emission scenario. We got reductions in rainfall of 70%, so it looked like it was going to be much drier in summer. But what we actually discovered when we did this, and we tried to look at a probability distribution. So what we did is, instead of running one model, we ran lots of models. So we used our model and created lots of other models by varying the physical parameters in the model in a realistic way, and also comparing it with the models that are run by other climate centres to try and get an assessment of the uncertainty in the projections. And what we found was actually that very dry model is actually too dry. Our model was too dry. It dries out too much. The soil wasn't, for example, the soil was drying out too much. So actually it's somewhere between very dry and slightly wetter. So this way of looking at it allows you to assess it as a risk-based approach. So basically what you're saying is, I want to know what's going to happen in 50 years' time. And rather than just taking one projection, I'm going to look at a probability of what's going to happen, and I can use that in a risk analysis. Because if you think about trying to plan 50 years ahead, it's always going to be a risk analysis anyway, because there's so many other uncertainties. We don't know how human population is going to change. We don't know what technologies are going to come along. And so this is just another one of those things that we don't know exactly what's going to happen, but we can give some idea of what's going to happen. So it's likely that it will dry, but we don't know by how much. So these models, you can see it doesn't. The squares on that are the grid boxes that we have for the model. And you can see we're not getting very much detail in there, and as well as not being able to give the detail for the people interpreting the results, that also means we can't capture the detail of the physics that's happening in the atmosphere. And so one of the things that we want to do is to run models with really high resolution, and we've managed to convince the government to give us some money to have a much bigger supercomputer. Some of that is to improve the weather forecast, because that's obviously has a big impact, but a large chunk of it is also going to help us to do climate projections, so that we can actually run some climate projections with a model that we would normally use for weather forecasting. Now this particular model we could only run it for England, southern England and Wales. It was too expensive to run it for the whole of the UK. With our next computer we'll be able to run it for the whole of the UK and run it for much longer. And in fact, the person, it took about 10 months, I think, to run this. But we are starting to do a bit of collaboration with scientists in Wales who are using some of the outputs of this, and we're working with other groups as well to use this as a resource. But just to give you the kind of headline results, really, if you look at the winter rainfall, so that's the kind of models that we normally run, and there's 12-kilometre models on the left-hand side. So these have got grid box, it's divided up into boxes of 12 kilometres across. And the one on the right is 1.5 kilometres. And you can see for winter, it doesn't make a huge difference. You've got the winter rainfall is increasing. But when you look at summer, this is looking at heavy rainfall. It's not looking at the average, it's just looking at the heavy rainfall events. in summer you can see that there's a big difference. So you're getting much bigger increases in heavy rainfall in summer. And that's what you'd expect. So when in the summer, when it's hot, you get convection. So you get the smaller scale clouds where you get rainfall over small areas. And that convection, as it gets hotter, you expect more convection, you expect more of that heavy rainfall. And that's exactly what we see in those models. So that allows us to look at that. A paper that was published, I think, last week actually showed that for temperatures that are very high, so where the average temperature for the day goes up to above 22 degrees centigrade, which is much warmer than you get in the UK. It's the sort of thing you get, if you think about nighttime temperatures, it's sort of 20 degrees, that's pretty uncomfortable. We don't get that very often in the UK. But if you get to that level, you actually get a decrease in heavy rainfall. So this is, at one level you're getting an increase in heavy rainfall, but when you go beyond a certain point it's actually decreasing. So there's some really interesting subtleties going on here. So there's a change, and it just illustrates that this is very non-linear. It's not just a simple, the temperature goes up, therefore this happened, the temperature goes up a bit more, therefore it happens worse. It's actually different. So that's one of the things that we can start to explore with a model like this, as to how the complicated physics actually works in practice. So as I mentioned, we need big high-performance computers to be able to do this. And I mentioned about the summer heavy rainfall rates. So this is just an illustration now of what a future landscape might look like. So this is a picture of a typical farm landscape in a flat area, and the sorts of crops that you'd normally see growing. And this is what it might look like in 2050. So you can imagine you're growing more biofuels crops. You're able to grow different food crops. So this is sunflowers here, and you've got a farm-scale biofuel power station, and you've also got, there's a wind farm in the background there as well. Now, of course, a lot of this picture was made in 2000, and it's just an illustration, really, that already some of these things you're seeing. So I've seen miscanthus growing in Devon, for example, when I've been out walking, and obviously we see wind farms around the place. There are, of course, now discussions about actually if you grow too many biofuels, you're going to displace natural ecosystems and you're going to displace food crops. So actually, how much biofuel is it sensible to grow? And I think this is now, a lot of the discussion around climate change is now also going to looking at climate change in the context of other things, that actually it's no good just saying we've got to solve climate change. We do have to look at it in the round, because what you don't want to do is create another problem by solving solve one problem and then create another problem. So, but this kind of picture illustrates the sorts of conversations that people are having. So I was going to illustrate also what how the impacts of climate change can actually impact on not just agriculture and all these sorts of things, but how it can impact on global trade. So this is relates it to human dynamics, and this is a piece of work that we did in collaboration with other organisations. And so it's showing the population is the purple, so and then you've got water stress is that kind of brown sort of colour. So this is the present day, so areas that are already water stressed. Trade, so you've got export and import, and it's just showing excuse me. Basically, it relates to food crops and where they're mainly produced and consumed. And you can see that there's, large production areas in some parts of the world and consumption in other parts of the world, and which are obviously going to be affected if the way that we grow crops has to change. Areas of fish catch. So these are all relate to places that export a lot of the things that they produce. And there's glaciers on there as well. Tropical cyclones obviously have an impact. So they would have an impact on the way that obviously people live their lives, but also on the way that you transport things as well. And then there's the fragile states marked on there, primarily in Africa. Ports and airports and shipping routes. So you can see there's a whole network of things going on here. And so I'm just going to illustrate just for one part of the world. So this happens to be for Southeast Asia, just because I happen to give a talk there, so that's why I've included that one. But it just gives. So these are it's just a little bit more detail about those things. You've got areas of high water stress. It's a very important region for rice exports and fishing. It's obviously exposed to tropical cyclones. It's a significant maritime transport region, and it's got an increasing population. So what about the future? So they're likely to have an increasing number of drought days, decreases in maize yield, and this particular study shows an increase in rice yield. It's interesting, when I showed this to some agricultural experts in the Philippines, they said, wait a minute, our study doesn't show that. Our studies show that rice is going to decrease, because actually the way that rice behaves is quite complex, and this particular model has simplified that too much. So it does show that the devil is in the detail with these things. What this type of analysis does, which is global, is to open up the conversation to say, these are the sorts of things that might happen, and this is what you might want to look at in more detail. But actually you do then need to drill down and look at more detailed local studies as well. So increasing water demand for irrigation, and that's water demand because of increased evaporation is driving water demand. You also obviously have increased water demand because you're growing more crops. That's not included in this analysis, but it's an additive effect. Decreasing runoff, so that's just a decrease in the amount of water flowing through into the rivers, which obviously has an impact on water that's available. Increasing temperature of the warmest days, an increasing flood frequency for most areas, and an increasing population exposed to coastal flooding. Part of that's because of sea level rise, part of it's because of population growth. So, just to summarise, I've talked about how the climate system works. I've shown you evidence that climate is changing, and that it's increasingly difficult to know what to expect. We've seen that there are changes in the number, frequency and strength of extreme events over a long period of time, and we're starting to be able to look at the attribution of individual events, although this is harder. I've shown you that the impacts of 4 degrees are not twice those as for 2 degrees, and obviously how we can change that is reducing emissions and improving resilience. So it's not just about reducing the greenhouse gas emissions, it's also about making sure that we're resilient to current weather and changes in the climate that are coming in the future. So making sure we've got the right flood defences, and making sure we don't build in the wrong places, making sure that if people are vulnerable to heat waves, that they have the right mechanisms in place for that. But equally, there'll be fewer cold days, so that helps people as well. So, and I'll leave it to you to discuss what this means for Wales. But I was just going to finish by showing you the Vostok ice cores, which gives you. So this is going back 400,000 years, and this is the temperature change. So and then underneath we've got the CO2, and you can see if you overlay those that they overlay very strongly. If you then look at what's been happening in the last 150 years, that's the temperature change, which is taking us outside of that range that we've seen over the last CO2 change, over the last 400,000 years. And then if we take that forward into the future, so this is now, I've just reduced that down so I can fit it on the diagram, and this is the projection for 2100, and I'll leave that up on the screen. So.